So now we're moving into the second chapter of this course. In this chapter, we're going to look at the harmonic analysis on commutative locally compact Hausdorff groups. So being commutative, it means it's very similar to what you see in the classical harmonic analysis. That's kind of the main goal of this chapter. We're going to see a lot of the results from your classical harmonic analysis, including the Fourier transform, the Fourier inversion, those kind of things still hold if your group is commutative. And we're going to develop a theory called the dual group or the character group of a commutative group. And then the main result is going to be this big theorem called the Pontryagin duality. Basically shows the double dual group is the group itself. Okay, so that's kind of the overview of this entire chapter. And the goal later on is that in the next chapter, we're going to look at the analysis on compact but non-abelian locally compact groups. So when your group is non-abelian, but if it's compact, then things get changed a lot, and you will see that the way we deal with these two objects are quite different. Okay, so that's kind of the idea for the next two chapters. So in order to develop some theory for these commutative locally compact these analysis, I need to briefly talk about commutative Banach algebra. So if you are going to take a pure math A10, which is the course on Banach algebra and operator algebra, you will see this probably in the first few weeks of the course. I'm not going to give you too much detail because if you want to learn more on the Banach algebra, you should take that course, and you'll certainly introduce much deeper results. So I'll just briefly go over kind of the idea behind the commutative Banach algebra. So why do we care about the commutative Banach algebra is the following, is that recall that we show the following. So if G is abelian, locally compact Hausdorff as well, then that's actually if and only if the L1 of G is a abelian, so it's a commutative Banach algebra. Okay, so let's first develop some theory for these general commutative Banach algebra, and then the L1 space will tell us a lot about this G. Okay, so that's kind of the idea. All right, so let's forget about this underlying group. Let's just start with a commutative Banach algebra. So let's let A with, let's say, some norm be a commutative Banach algebra. So let's just say B algebra. So in other words, it has this the norm of a product is less than or equal to the product of the norm, and it's a Banach space itself. All right. So let's first make some definitions. So whenever you have a Banach space, you can talk about the linear functional. And we say a linear functional is multiplicative. So a multiplicative linear functional. Let's say, give it a notation, let's say phi from A to C is essentially defined as basically a linear functional. Okay, so of course it's linear functional, and that's multiplicative. Okay, very descriptive. So what do I mean by multiplicative is that is basically what we expect it to be, because you have an algebra structure here. So you can talk about phi evaluate on the product. Being multiplicative means it's just respect this multiplication. So phi of AB is equal to phi of IB. And we usually assume that phi is non-zero. Okay, of course, if your phi is zero, it's clearly multiplicative. Okay, let's just ignore that case. All right. So let me give you some fact. Okay, so I'm not going to prove that. If you're interested, you can pick up any Banach algebra book or operator algebra book. Okay, so they will probably have these facts. So whenever you have a multiplicative linear functional, then it always have norm 1 actually. So phi is multiplicative linear functional. Then you always have phi is actually equals to 1. And in fact, you don't even need to assume it's a linear functional as long as you have a linear homomorphism. Okay, it always have norm 1. Okay, the continuity actually only just follows from the linearity and the multiplicative. All right, and the second fact is the following. So if you consider the kernel of phi, so phi being a linear map, you consider all the element A where this phi A can map to 0. And you can convince yourself this is going to be a closed subspace of A. Okay, so that's fairly clear. And moreover, it's going to be a closed two-sided ideal. Okay, it's a closed two-sided ideal. So why is a two-sided ideal? Well, when you multiply something on the left or on the right, the phi of that value, because phi is 0 and phi is multiplicative, you have that is still inside the kernel. So this is going to be an ideal. And moreover, in fact, so because this kernel phi looks like the kernel of a linear function, so it kind of have codimension 1. So it's not only a closed two-sided ideal, but it's also a maximal ideal. Okay, so I'm not going to give you the definition, but it's actually also a maximal ideal. So the maximal ideal is essentially just any bigger closed two-sided ideal containing this ideal has to be A itself. Okay, so this is sometimes these phi we also call the maximal ideal space. So let's just let this M of A to be all the multiplicative functional. So phi, where phi is multiplicative. Okay, and we can consider phi as a subset of the dual space of A. Okay, so a lot of the time we also call this the maximal ideal space. Okay, so this also called the maximal ideal space. All right, so in fact, they're in one-to-one correspondence. Whenever you have a maximal ideal, two-sided ideal of A, then you can always find a linear function using some Banach argument. Okay, this should be fairly simple. And then conversely, whenever you have such a multiplicative functional, and then you can find this kernel space is also a maximal ideal. Okay, so they're sometimes used interchangeably. All right, so let's give, first of all, let's do some propositions. So it turns out this maximal ideal space, or the space of all the multiplicative linear function itself, because it's a subset of A star, okay, the dual space, okay, you can make them into a locally compact space. And in fact, you can say slightly more about that. So here's a proposition. So it turns out this M of A, the maximal ideal space, is always locally compact. And also you have that if, moreover, if your A is unital, then this space is actually just compact. Okay, so here's the fact. So M of A, you do the because it's a subset of the dual space, you put a weak star topology on the M of A. That's the default topology on your maximal ideal space. All right, so now here's let's prove this fact. So let's assume that the following. So let's let MA 0 to be all the multiplicative ones and union the 0 functional. So 0 is technically also multiplicative. All right, so we know this is going to be closed. Okay, so then this MA is going to be closed in the A star. Okay, so you can convince yourself because you have the weak star topology. Everything is multiplicative. You have a mat that's also going to give you something that's multiplicative. Okay, so I'll just leave it as an exercise. Okay, so why it's closed is very simple. And because it's closed, okay, so I have the very nice result of Banach log glue. So because you have that this MA0 that's going to be contained inside the unit ball of the dual space of A, and the dual space of A is this one is going to be weak star compact by the Banach log glue theorem. Okay, a log glue. So basically, MA0 being a closed set as a subset of there, so it's going to be compact, Hausdorff, and locally compact. Okay, so you can convince yourself that's why MA0 is going to be a subset, so that's compact. You remove the 0, so you get something that's locally compact and Hausdorff. Okay. All right, so this finished the proof. You always have a locally compact topology on your maximal ideal space. Okay, that's just inherited from the weak star topology. And so when your A is going to be unital, so when let's say A is unital, so you want to show that the MA is compact. Well, the idea is that your MA is essentially just the MA0 remove the zero functional. Okay, so you want to show that your zero functional is kind of separated from the rest of it. And what you can show is that, well, because A is unital, you can think about, let's say, 1 in A is the unit, it's the multiplicative unit. So you have the phi 1, if you take any functional on this in the maximal ideal space, it has to return a value of 1. But the zero functional, when you evaluate at 1, well, because it's zero functional, it returns 0. So as you can see, if you have a bunch of phi alpha inside the MA, and if you have a phi alpha converge to some phi, then because of the weak star convergence, your phi of 1 is going to be 1. It's never going to converge to the 0 thing. So your 0 functional is kind of separated from the other guys. So in other words, your MA itself is going to be weak star closed. So it's going to be is equal to this weak star closure. So it's going to be compact. Okay, so the topology is compact when A is going to be unital. All right, so this finished the proof. So basically, the idea is now we have a topology on the maximal ideal space. And one goal of the kind of the basic theory of the commutative Banach algebra is this big theorem called the Gelfand transform. So essentially, it's saying, well, suppose now I have this MA, which is locally compact. So this A is kind of related to the continuous functions on these MA, okay, or sometimes you see zero function, okay. So that's kind of the often in time this A is going to be related to those functions, and how do you relate them is by this very nice transformation called the Gelfand transform. So here's the definition. So let's consider for every A inside A. All right, so I can define a map. So let's let a hat to be equals to a function. Let's consider a function from the maximal ideal space to the complex number by doing the following, doing exactly the evaluation A. Okay, so you map a functional phi, a multiplicative functional, map it to phi of A, the evaluation map. Okay. So this, in other words, your A hat of a phi is equals to phi of A. Okay, so this map A to A hat is called the Gelfand transform. Okay, the Gelfand transform, and this is kind of the key transform of these commutative Banach algebra. And the reason is the following. So let me just state this big theorem due to Gelfand. Okay, so let's let A to be a commutative Banach algebra, say B algebra. And so you have this Gelfand transform. Let's give it a name. Let's call it phi. Okay, so phi is from maps A maps to this A hat. So you can think about this A as inside A, and this A hat is some function on the maximal ideal space. Okay, so it turns out it's going to be inside the C0 of the maximal ideal space. Okay, so this map is actually a contractive. So meaning is norm is going to decrease, and it's a homomorphism. Okay, so homomorphism. Okay, so it's contractive essentially is just saying phi of A, which is equals to basically A hat, is norm. Basically that's the sup norm on the C0 of the maximal ideal space. Okay, that's going to be less than or equals to the original norm A. Okay, so there are certain conditions when this is a equality, but we're not going to get there. But in any case, this is the first part of the theorem, and moreover, I also have that this image, the phi of A, so that being a algebra of functions on the C0 MA, so that's going to separate point. Okay, so they separate points. Okay, The proof, I'm not going to go over this proof. Okay, you will learn this when you take the pure math A10, or you can pick up an operator algebra book. Okay, so I will skip the proof. So the proof, let's say omit it. Okay, that's beyond our course. We don't really care. But the idea is now is the following. So now let me talk about why we introduced this in the first video of this chapter is that we saw that when G is a billion, okay, we talked about when G is a billion, that's even only if the L1 of G is a billion, and we know the L1 of G is a Banach algebra, so it also has a Banach algebra structure. Well, in fact, we proved it has a Banach star algebra structure, but let's only care about the Banach algebra structure for now. And so because it's a commutative Banach algebra, I can now talk about the maximal ideal space. Okay, so I will have a maximal ideal space of the L1 of G. And it turns out it has a very nice description. Okay, so this turns out to be isomorphic to the dual group, okay, the G hat. Okay, so this is what it does is essentially all the continuous homomorphism from G to the unit circle. Okay, so that's also defined as the character group. Okay, so I'm going to show in the next video, we're going to look at this character group. Okay, so all the homomorphism from G to the unit circle, it turns out they're exactly the maximal ideal space for the L1 space as a Banach algebra. All right.